everybody, and welcome back. So, for today's topic, we're going to be looking at more derivative rules. Towards the end of the first unit, we looked at power rule and some other function types. So, we looked at sine and cosine, their derivatives, exponential functions, logarithmic functions. So, this whole unit, we're really just focusing on adding more tricks to our bag of tricks for evaluating the derivative of any function, really. So, by the end of this unit, we should be able to tackle just about any kind of function that I can throw at you, and you should be able to find the derivative for it. So, to that end, today we're going to start off by looking at the other four trig functions. So we know sine and cosine, and now we're going to talk about the derivative of tangent, cotangent, secant, and cosecant. So there are all kinds of ways to talk about these and look at this. One of the neat proofs for finding the derivative of tangent, so you guys see it right here, it says that it's secant squared, but there's a pretty simple proof for this because if you guys remember, if I started with the function y equals tangent of x, I could actually rewrite that as sine of x over cosine of x. So to take the derivative of that would actually require a quotient rule, where I have sine of x's derivative is cosine, cosine of x is negative sine. So when I do my insides minus my outsides, my dy dx would result in cosine squared minus, or excuse me, because we're subtracting this negative product, it becomes plus sine squared all over the original denominator squared, which is cosine squared. And then from pre-calc, we know one of the really important trig identities is that Pythagorean identity that says uh, sine squared plus cosine squared equals 1 squared, or 1. Again, that's the idea of the x coordinate plus the or squared plus the y coordinate squared equals the hypotenuse squared, or the Pythagorean identity. And those coordinates refer to the sine and cosine values on the unit circle. So this whole value of the numerator can be replaced with 1. So if I'm left with 1 over cosine squared, one more trig identity, the reciprocal identities, says that that is equivalent to secant squared. We have a similar proof for cotangent, where we essentially just flip-flop these guys. We end up with a negative 1 over sine squared, which results in negative cosecant squared. Secant and cosecant, they have proofs as well. They're far more complicated um, and require some other rules that we haven't quite learned yet to prove them. But there are similar proofs that we can prove how we go about getting these results. So these are rules that you guys need to commit to memory. Some ways to help you guys, the way that they're ordered here. Tangent and secant have a derivative function relationship where tangent's derivative yields something to do with secant. Secant's derivative has something to do with tangent and vice versa. Same thing pairing cotangent and cosecant together. So it is a little tricky. If you notice, the tangent and cotangent, both of their derivatives are a function squared. You just have to remember which one they're paired with. Secant and cosecant's derivative actually yield a product of that function and its counterpart. So secant x's derivative is secant x tangent x. Cosecant is negative cosecant x times cotangent. Another thing to point out, notice the C functions, cotangent and cosecant, just like cosine, all three of the co-functions, or the functions that start with that C, have negative derivatives. So that is a really important piece to keep in mind. That's an easy way to help you guys memorize this. But before we dive into examples, I want to take a look at the relationship between tangent and secant squared, just to kind of hit home the importance of understanding how a derivative's y value relates to the graph of the original function. So what I've got here, I've got a lot of stuff here. So let me break it down one piece at a time. So first off, red graph here is our tangent of x graph. Remember, it has vertical asymptotes at the pi over 2's, negative pi over 2, pi over 2, and so on. But then in between those asymptotes, we have a graph that's always increasing. It actually resembles the x cubed graph. It's not exactly that, because the x cubed graph, if you want to see it here real quick, it's super easy. The major difference is x cubed flattens out at the origin and then progresses to, or proceeds to increase increasingly. But this tangent guy, it has the same kind of shape. A lot of people mistake it as being a cubic in between, but it's not. It just kind of resembles that. But because this graph is always increasing wherever it's not on one of those asymptotes, remember that anywhere that the graph is increasing, that means that the tangent line would have a positive slope. So this little black graph here, I'm not showing you guys the whole tangent line because if I do that, it's going to cut over the rest of the graph, and that might be a little confusing. So if you wanted to see, that is the whole tangent line, but sometimes it's helpful just to imagine a little piece of it. So looking at that piece, you guys can tell that that line has a positive slope. It's increasing from left to right. So as I progress across this graph, you guys can see what happens. So I'm going to start closer to negative pi over 2. Right now, that looks like it is vertical, and that's because, uh, remember, when a graph is really steep, the slope is very large. So that is where that slope is going towards positive infinity. So on the left side of the graph, we have really big positive slopes. And as I work across this graph, we're still increasing, so we still have positive slope, but the graph isn't increasing as quickly. So the slopes are actually getting smaller as I work across this graph. So that tangent line is going to flatten out. It's not going to flatten out completely, but as we get towards the origin, right there at the origin, that slope is actually the smallest slope, or that is the least steep that tangent line ever gets. Because immediately after that point, the steepness of the graph is going to start increasing again. So that tangent line is going to get steeper, or the slope is going to increase. So as we continue across, the graph gets really steep, and so on. So again, this is the original function, f of x. So we know now by the derivative rules, the derivative of tangent is secant squared. So that means that all the descriptions that I just gave about how this graph changes should be represented by the graph of the derivative. So if we kind of go back here again, now I'm going to show you a point on here. So these 2 points, now that you guys can't see them right now because they're off screen, but in a second, you're going to see a point of tangency on the red graph and then another point on the graph of g of x. And that point is representing the slope of that tangent line. So what I want you to do is keep an eye on a couple things. They're going to come into screen. So this point right here, the y coordinate there is the value of the derivative at this particular x coordinate. So what it's saying is the y coordinate here is 5.268. That is the slope of this tangent line. That's what this number is down here. So when we look at the graph of the derivative, whatever that y coordinate is at a point, it is directly corresponding to the slope of the tangent line on the original graph. So like we said, near this asymptote, the graph is very steep. That's why you guys can't see that point because the y coordinate is way up top here. Right now it's at 17.6. And as I move across this tangent graph, the tangent line is flattening out. So the slope is getting smaller. That's why this derivative graph is actually coming down. So the y values are getting smaller. And when we get to the origin, the steepness of this graph is the smallest that it ever is, which is why this graph bottoms out and has a minimum. And then we start to increase our slope again, and the graph is getting steeper, which means the y value of the derivative is getting larger and larger. So this is true. This relationship is true for every function and its derivative. I just chose to point out some of the features here that we see with the tangent and secant squared. But we can do the same kind of relationship really for any function. If I wanted to look at cotangent and its derivative, which is negative cosecant squared, and we see the same kind of relationship. Now I'd have to adjust our window here, but it still works the same way. That the asymptotes are shifted on cotangent. So the cotangent graph is the opposite. It's always decreasing. And as we head towards this turning point here in the middle, this represents where the graph is least steep. But because it's negative numbers, it's actually where the graph or the y values on the derivative are closest to 0, because small negative numbers are close to 0. Steep negative slopes would be really big negative values, so further from 0. So again, this relationship is something I'm going to hit on as we progress through this course because it's that important. It's really important for us to understand these special relationships between the graph of a function and the graph of its of its derivative. All right, so now though, if we want to try and practice using some of these derivative rules, we're just going to dive in here. So remember, multiple terms means we take the derivative of each one individually. So we have y equals x minus tangent of x. So dy dx would be derivative of x is 1 minus derivative of tangent is secant squared. So with trig always comes some of those trig identities. So if you guys remember, um, the Pythagorean identity that we just used a second ago has alternate forms that are found by transforming this original guy. So if I were to take this guy and divide everything by cosine squared, we end up with tangent squared x plus 1 equals secant squared x. So there are special relationships between all of these where we can actually transform this guy a step further, and we end up with tangent squared is equal to secant squared minus 1. That is actually the exact opposite of this derivative. So if we wanted to, that means this derivative has an alternate form of negative tangent squared x. That is not something that's necessary, but sometimes when we're working towards a particular answer, we may need some of those tricks to manipulate the form of these trig derivatives. All right, for the second one, we have y equals x times secant x. So this would be a product rule problem. So let's set this up for pieces. First function x has a derivative of 1. Second function secant x has a derivative of secant x tangent x. So again, it's just going to take you guys some time to be familiar and comfortable with these four new rules and memorizing them. But again, it's just one of those automatic things when you see each of those four functions we need to know what their corresponding derivative is. Then now we're going to take insides plus the product of the outside. So we get dy dx equals, insides would produce secant x plus outsides. Again, we have a non-trig thing being multiplied by trig function. So in this case, it's pretty direct that the order should be this guy first. But please make sure, even if it was reversed, always put the non-trig factors in front of the trig functions. So this will result in x times secant x tangent x. So for right now, all we need to do is find the derivative. But if this was one of those situations where putting it in a different form or factoring it would be helpful or necessary, one possible alternate form of this guy would be pulling out the factor of secant x from both terms here, and we would be left with 1 plus x times tangent x. So I'm not saying that that is necessary. Both of these would be acceptable answers for this derivative, but just be aware. I want you guys to see all those different ways that we can manipulate these answers or rewrite them. All right, now for the next one, we're going to do something a little bit different. So the original function that I want to take the derivative of is this guy, y equals 1 minus cosine of x over sine of x. So looking at that right off the bat, it's a fraction. We've got trig over trig. So it looks like we would need to use the quotient rule. And this is a case where, because they're not both polynomials, remember in the last section, in the last video, we talked about how a lot of times it may look like it's a quotient rule, but there are ways to manipulate it so that the quotient rule isn't necessary. This is a case where technically it's not necessary, but you wouldn't be going down a bad road if you decided to do this guy with the quotient rule. Because whenever it's not polynomial functions, sometimes the quotient rule is just as easy as an alternative form. But when we're dealing with trig, a lot of times those trig identities come into play. It can kind of change things up for you. So if we take the original guy in its original form, we have 1 minus cosine. The derivative of cosine is negative sine. So the derivative of negative cosine is positive sine of x. And then our denominator function sine of x has a derivative of cosine of x. So remember, it's a quotient rule. So we're going to do insides minus the outsides. So for this one, our insides are pretty straightforward. That produces sine squared x. And remember, sine squared x, just want to give you guys some of these little reminders of stuff that you may not have dealt with in a while. Remember that when we write that notation, sine squared x, it means the same thing as the sine of x quantity being squared, or taking sine times itself. This is just the shortcut way of writing it. It's an alternative to the group parentheses, because what happens a lot of times is you guys will not remember to put the parentheses and write it that way. That is actually meaning sine of argument x squared. That's a very different thing. So just keep that in mind, okay? I just wanted to remind everybody of that. But we have sine squared minus, I'm going to write this guy in the long form here. So cosine times that group of 1 minus cosine. So I'm doing it that way just to show you what's going to happen here. So, and then remember our denominator squared, it goes on bottom. So I need to distribute here. So I'm going to send that guy into both of these. So we end up with dy dx equals sine squared of x minus cosine x, and then plus cosine squared x all over sine squared x. All right, and now what we're going to end up with is our, if you look at it, we have two parts of our Pythagorean identity. Remember, sine squared plus cosine squared equals 1. Well, those two parts are kind of hiding here because they're being separated, but they're still being added. They're both positive, so it's still equal to 1. So I'm going to replace those two with 1, and my result is dy dx equals 1 minus cosine of x over sine squared x. Okay, now I'm going to leave that alone for right now. We're going to come back to it. And I want to go back to the original. So one way to rewrite this guy is using one of our little tricks from a couple sections ago. We have a numerator that is two terms, 1 and then minus cosine of x, and then we're being divided by sine of x, one term. So remember, when it's multiple terms over one term, we can actually break it apart into separate fractions. And that would have resulted in 1 over sine of x, which can be converted to cosecant x, minus cosine over sine, which can then be converted to cotangent. So that's where this alternate form of the function comes from. So if we rewrite the original into just these two functions, then we can just take the derivative using these new rules. So cosecant x, again, it starts with a c, so the derivative is negative, and then this guy will result in cosecant x cotangent x, and then minus cotangent derivative. Again, it starts with a c, so it's a negative, which means this actually turns into a plus, and then cotangent results in cosecant squared x, which means I could rewrite this guy as, if I wanted to, I could pull a cosecant out from both of these. A lot of times you'll see a negative pulled out so that this first term is positive, but that leaves me with cotangent minus cosecant x. So there's several different forms here, different ways that we can manipulate this. But now I want to go back to the original form. So we have two equivalent forms that we started with, but the derivatives look very different. And that's because the original form's derivative is dealing with sines and cosines, but the other guy has all these reciprocal functions in there. Well, if you remember, one of the things that you learned about in pre-calc was rewriting these trig expressions using sines and cosines. So what we're going to do is going to manipulate this original guy and see if we can't actually go the other way and transform it into this result. It can work either way. We could start with this guy and go backwards, but this one's a little bit more fun to work with. So to do that, we're actually going to use the same property that we used up here to rewrite the original. I'm going to separate this guy, and it becomes 1 over sine squared x minus cosine over sine squared. So the 1 over sine squared should jump out at you. That is actually going to turn into cosecant squared x, or this guy. So we have that part, but now somehow this fraction needs to turn into these two functions being multiplied. And to do that, we have to use another special trick. So this isn't something that we use all the time. It's specifically something that pops up with these trig functions. And what it is I'm going to split this denominator into separate factors. So I'm going to do that. Let's do that over here. So I've got negative cosine of x over sine of x times sine of x. Well, 1/6 is the same thing as 1 over 3 times 2, or 1/3 times 1/2. Again, all these numeric properties or steps that we use can go in the opposite order. So if I started with two fractions being multiplied, we just multiply straight across, and it results in 1/6. So that's what we're doing here. We're going to do the reversal of this. So I'm going to actually separate this into negative cosine x over sine of x times 1 over sine of x. Well, cosine of x over sine of x is cotangent. 1 over sine of x is cosecant, and that negative sign, oops, that negative sign out in front, it doesn't have to go in this order. It could be -1 times 1 over sine, and then the cosine over sine. So we actually have all three of these pieces. So what that does is that proves to us that this result from the original form can, in fact, be transformed into the result of our alternative form's derivative from the second side. So all that is to say that these trig problems can be done a million different ways because it always comes down to these identities, and there's so many different ways to rewrite them that odds are you may think of a different way to do it than the person sitting next to you. You guys may get totally different answers, but it doesn't mean that one of you is wrong. It's actually just saying that one of you is not done yet. You haven't reached the same point because you have to do some transformations with those identities. All right, so that's about all we're going to talk about as far as our trig functions go for right now. And now we're going to turn the page to some higher order derivatives. So a derivative function represents how another function's outputs change with respect to their inputs. So as I make x bigger, how does y change? That's in general what a derivative function represents. But sometimes we're going to be interested in how the derivative function itself changes. Or in other words, that means we need to be able to find the derivative of a derivative. As long as the derivative function itself is differentiable, or in other words, its graph can, we can calculate the slope or the rate of change of the derivative function's graph. Remember, that's what it means to be differentiable. Then we're able to reapply all of our known rules to take the derivative as many times as we need or want. And so there's a lot of applications to this because if our derivative function tells us how f changes, then the second derivative is going to tell us how the first derivative changes. But that also has implications about the original graph. So if you think about it, we've already looked at different things about the connection between f and f primes graph. Remember, this tells me how f is increasing or decreasing. That's the job of this first derivative function. Well, we've also talked about how whether the original graph is getting steeper or not. So when a graph is getting steeper, that is telling you that f prime is actually changing. So it's not just a matter of am I increasing, but am I increasing in a faster way, like the graph continues getting steeper and steeper and steeper, or is it flattening out? If it's flattening out, the overall graph of f could still be increasing, but it's doing so in a slower manner. So there's all kinds of connections between all these graphs, especially when you get into the physics world. So to give you a little bit more background, Isaac Newton, he developed this system of calculus to help explain his model of physics and help with all the math. So there is a very close tie between the realms of calculus and physics. And a lot of these higher order derivatives have a lot to do within that realm of physics. Now, notationally, what you guys need to be worried about, it depends on what the original form looks like. There's multiple ways to write these. In the function notation, which we use a lot, remember the prime symbol is what indicates that it's a derivative. So if I take the derivative of that function, then we add another little prime symbol. That is the f double prime of x, or the second derivative. The same is true for f triple prime, or the third derivative. But after that, we don't want to keep like putting a ton of tick marks up top there. So after the third derivative, you'll see just a little number within parentheses. It's important that you put parentheses up there so that we know or we don't mistake it as some kind of exponent. Okay. Now, for y, there were two notations that have become custom. One is this dy dx notation. So dy dx represents the change in y over change in x. But for the second derivative, we want to look at the second change of y as x changes twice. So one way that I've come to help students understand this is remember the notation of d dx. This tells me an operation to do. It tells me to do the math of finding the derivative. Now, this isn't exactly why, but notationally, if you really look at this, this is kind of like there are two d's, so we write d2y, but there are two dx's, so we put the 2 after the dx. So that, again, that's not exactly why, but it does help students a lot of times understand that notation. So we read this as d2y dx2, or the second derivative, d3y dx3, and so on. That notation is nice because we don't have to worry about like tick marks or anything like that. We just use that consistent pattern. But then we do sometimes also use the prime notation with just the y variable, so y prime, y double prime, and so on. So if we're using that notation, we use the little numbers once we get past the third derivative. So that's the notation side of it, but mechanically, how we actually go about doing it, there's not really anything special. Once you have the equation for the first derivative, you just do the process over again for whatever result we end up with after the first one. So let's dive in and try some of these. So I've got f of x equals 3x to the fifth minus 7x cubed plus 9, and we want to find f double prime. Now, for a lot of functions that we work with, there is no restriction on how many derivatives you are able to take. The one exception to that is actually polynomials. So the reason that polynomials have restrictions is because the only rule we use here is the power rule. And the power rule says when you take the derivative of x to the n, you have to deduct 1 from the exponent, which means whatever the largest degree of your original polynomial is, that is what's going to dictate how many derivatives you can actually find. Because if I start with an x to the fifth, its derivative is some x to the fourth, 5x to the fourth. Its derivative would be 20x cubed, and then 60x squared, and 120x to the first, and then 120 just the constant, and then 0. But once we get down to 0, then there is no derivative of 0. If there is no quantity, then there is no point in talking about its change. So polynomials are the only kind of function where you're actually counting down every single time. So there's a limit on how many derivatives we can find. And if you just count them up, this is our f. This would be f prime, f double prime, triple prime, fourth derivative, fifth derivative, and then finally our sixth derivative. So the rule of thumb is if we have an nth degree polynomial, then you are actually able to find n plus 1 derivatives without running out. So that's just something to keep in mind when we are working with these polynomials. But to find it, we just really do the process twice, or in this case, twice, because it's the second derivative. So for our first derivative here, we would have 15x to the fourth minus 21x squared, and the constant disappears. So then our second derivative, we just start over with this new equation, would yield 60x cubed minus 42x, and that's it. That is our second derivative, or f double prime of x. All right, next one. Now I want to find f triple prime. So polynomials count down because their derivative rules say that we have to lose 1 in the exponent. But if you think back to all the other functions, all of the other functions had a function of a similar type of form to it, or they had derivatives that we're not limited on how many times we can do that. For cosine, it's just going to continue bouncing back and forth between sine and cosine, because the derivative of 5 cosine is negative 5 sine of x. And for the exponentials, every exponential function has a derivative that is also an exponential function. So that is an infinite loop that just continues on and on and on forever. So the derivative of 6e to the x is 6e to the x. F double prime, derivative of negative 5 sine of x would be negative 5 cosine. Derivative of 6e to the x, this is just going to repeat itself forever. And then negative 5 cosine, its derivative, because it's already negative, actually going to change signs to become positive 5 sine of x plus 6e to the x, and then that's it. That is our third derivative. So this would be an example because this is a trig and an exponential. Those two, their rules just say there's always going to be a derivative of that next order. So we can just keep going on and on forever. All right, so I have y equals 2 secant x, and now I want to find d2y dx2. Again, you can think of that as the second derivative of f, or y prime. Those are the similar notations. But again, we just need to be able to look at the notation and tell how many times I actually need to take that derivative. So in this case, y prime or dy dx, however you guys want to do it, or actually, excuse me, because they specify d2y dx2, we should stick with that notation. But dy dx would give me 2 secant x tangent of x. And then to find that second derivative, this is now going to turn into a product rule. So we got to go back to the last section and use that rule. So we get 2 secant x tangent x again. and then tangent x turns into secant squared x. So insides plus outsides would give me 2 secant x tangent squared x plus, on the outside, we actually get 2 secant cubed x. So secant times secant squared gives me secant cubed. And again, not that we absolutely have to do this, but just looking at this and seeing the common parts, it may be beneficial to us to factor out a common factor of 2 secant x, which leaves me with tangent squared x plus secant squared x. And there are more things that I can do with this guy because of that Pythagorean identity, but for the sake of what we're doing right now, it's not absolutely necessary to explore that. Oh, I'm sorry, we messed up my notation here. d2y dx2. So that is our second derivative. All right, now for the last one, I want to find y triple prime of this guy. So now for this first term, we have, I'm going to rewrite this as 6x to the negative third. Now, that requires the power rule. However, because I'm starting on the negative side of the number line for the exponents, as I use the power rule and continue to subtract one, I'm never going to end up at 0. So as long as you're starting with a negative exponent, the power rule is not restricting. We can take an infinite number of derivatives of that term. Now, for natural log, remember for natural log, we know that the derivative of natural log of x is 1 over x. This says 4x. We don't know how to do that yet, but we do have those logarithm properties that says the product inside the argument can be separated into their individual logarithms. Remember, we saw an example of that a couple sections ago, and when we do that, and take the derivative of it, remember that is just a constant. It's some decimal, 1 point something. And so the derivative of 1 point something is just 0. So that guy's going to disappear. Now for the first one, when I do my power rule, I get negative 18 x to the negative fourth plus 0. And then a natural log of x will turn into 1 over x. So natural log, or all logarithms, are another function where we can take an infinite number of derivatives because the derivative of natural log is going to turn into something that requires the power rule. So I'm not going to rewrite this guy without its negative exponent because I know I'm going to take another derivative. So there's no point in putting it back into final form and then having to undo that. So I'm actually just going to rewrite 1 over x as x to the negative first. So just like x to the negative third has an infinite number of derivatives, so does this guy. So for y double prime, if I do the power rule again, that would be positive 72 now, x to the negative fifth. This would be negative 1 x to the negative second. And then if I do the derivative one more time, 72 times 5 gives me negative 360. And my new power would be x to the negative 6. Bringing down the negative 2 here would turn into positive 2 x to the negative third. So my final form for y triple prime would be negative 360 over x to the sixth plus 2 over x cubed. And that is our final answer. And that's it. So again, higher order derivatives, it's really just a matter of recognizing the notation and knowing how many times we have to continue that process of finding those derivatives. That's it. You guys are all ready to go. Good luck with this section, and let me know if you have any questions.